13. Data windowing and creating baselines for deep learning. This section transitions from the theoretical understanding of deep learning models and initial data preparation to the practical steps required to feed time series data into these models. We will focus on two critical aspects: transforming raw time series into a format suitable for deep learning through data windowing, and establishing performance benchmarks using simple baseline models before diving into complex architectures. 13.1. The necessity of data windowing for time series deep learning. Deep learning models, particularly those designed for sequential data like recurrent neural networks, RNNs, LSTMs, GRUs, convolutional neural networks, CNNs, and transformers, typically expect inputs of a fixed size. However, raw time series data is often a continuous stream of observations. Data windowing, also known as rolling or sliding windows, is the fundamental technique used to transform this continuous stream into discrete, fixed-size input-output pairs suitable for supervised learning. Imagine a continuous film reel. To analyze individual scenes, you don't just look at the entire reel, you cut it into segments, each containing a sequence of frames that tell a mini-story. In time series, each mini-story is a window where a sequence of past observations, the inputs, is used to predict a sequence of future observations, the labels. 13.1.1 Defining inputs and labels in time series windows. For time series FO recasting, each window consists of two main parts. Input window, or look-back window. This is the sequence of past observations, code snippet, that the model will use to make a prediction. Its length is defined by code snippet. Label window, or forecast horizon. This is the sequence of future observations, code snippet, that the model is trained to predict. Its length is defined by code snippet. The relationship between the input window and the label window is crucial. The code snippet parameter defines the offset in time steps between the end of the input window and the beginning of the label window. For most forecasting tasks, the label window immediately follows the input window, meaning the code snippet is typically equal to the code snippet. Consider a scenario where we want to predict tomorrow's traffic volume using the last 24 hours of data. Here, the code snippet would be 24 hours, and the code snippet would be 1 for tomorrow's single-hour prediction. The code snippet would also be 1. 13.1.2 Common parameters in data windowing. To precisely define a data window, several key parameters are used. Code snippet, the number of time steps in the input sequence, code snippet. This is the look-back period. Code snippet, the number of time steps in the output sequence, code snippet, to be predicted. This is the forecast horizon. Code snippet, the number of time steps between the end of the input window and the start of the label window. If code snippet th, a label immediately follows the last input step. If code snippet, the label window immediately follows the input window. Code snippet, the total length of the window, which is code snippet. The label window is extracted from the end of this total window. Code snippet, how many steps the window moves forward each time it's created. A code snippet of 1 means overlapping windows, which is common. A code snippet equal to code snippet means non-overlapping windows. 13.2 Types of data windows and their applications. The method of generating windows can vary depending on the forecasting task and model requirements. 13.2.1 Sliding window, rolling window. The sliding window is the most common technique for time series forecasting. It involves a fixed code snippet and code snippet. The window slides across the time series data, moving forward by a specified code snippet at each step. This generates a large number of overlapping or partially overlapping input-output pairs. Application: ideal for most deep learning forecasting models where a consistent history length is beneficial and a large training set is desired from a continuous stream. Numerical example: consider a time series, code snippet. Let code snippet, code snippet, code snippet. This means we look at 3 past values to predict the next single value. Window 1. Input, code snippet, code snippet. Label, code snippet, code snippet. Window 2. Window slides by code snippet. Input, code snippet, code snippet. Label, code snippet, code snippet. Window 3. Input, code snippet, code snippet. Label, code snippet, code snippet. And so on. Visual description. Imagine a fixed-size rectangle moving across a horizontal line representing time. The left part of the rectangle is the input, and the right part, just after the input, is the label. 3.2.2 Expanding window. In an expanding window approach, the code snippet grows with each successive window, while the code snippet remains fixed. The model is given an increasingly longer history to make its prediction. Application. Useful when the model might benefit from all available historical context up to the point of prediction, or for tasks where the cumulative effect of past data is important. It's less common for deep learning as it results in variable input sizes, which often requires padding or more complex model architectures. Visual description. Imagine the left boundary of the rectangle staying fixed at the beginning of the time series, while the right boundary expands further into the series, always defining the input, with the label immediately following. 3.2.3 Fixed window, non-overlapping. A fixed window approach typically uses a code snippet equal to the code snippet, resulting in non-overlapping, contiguous segments of the time series. Application. Less common for general forecasting, but can be useful for specific analysis tasks or when memory constraints are severe, as it generates fewer windows. Visual description. IMA. Giant distinct, equally sized rectangles laid out end-to-end along the time series, with no overlap. 13.3 Challenges and best practices in data windowing. While conceptually straightforward, implementing data windowing correctly can present several challenges. Data leakage. This is the most critical pitfall. It occurs when information from the future, e.g., validation or test set, inadvertently leaks into the training set. 4 time series. This typically happens if you shuffle data randomly before windowing, or if your windowing process allows training windows to contain data points that also appear in validation or test windows. Best practice. Always perform train validation tests splits temporally before windowing. This means dedicating the earliest portion of your data to training, the next to validation, and the latest to testing, ensuring a strict chronological separation. Windowing should then occur independently within each of these pre-split datasets. Incorrect input/label alignment. Ensuring that your code snippet, and code snippet parameters correctly define the desired input-output relationship. E.g., using 24 hours to predict the next hour, not an hour within the 24-hour input, is vital. A common mistake is off-by-one errors in indexing. Computational overhead. For very long time series or very small code snippet values, generating all possible windows can be computationally expensive and memory-intensive, especially if windows are large. Feet. Your alignment. If you have multiple features, ensure that the windowing process correctly extracts all features for both the input and label parts of the window. To address these challenges and promote robust, reproducible code, it is a best practice to encapsulate the windowing logic within a reusable class. 13.4. Designing a reusable data windowing class. Creating a dedicated class for data windowing offers significant advantages. Standardization. Ensures consistent windowing parameters and logic across different experiments, models, and datasets within a project. Modularity. Encapsulates the complex indexing and data slicing logic in one place, making the main training script cleaner and easier to read. Reusability. Once written, the class can be easily reused for any time series forecasting problem, saving development time. Maintainability. If the windowing logic needs to be updated or debugged, all changes are confined to a single class. Abstraction. Hides the low-level details of window creation, allowing the user to focus on the model architecture and training. 3.4.1 Conceptual structure of the code snippet class. A code snippet class would typically take the raw data, already split into train, validation, and test sets, and the desired window parameters as input during initialization. It would then provide methods, or properties to generate batch datasets suitable for deep learning frameworks like TensorFlow or PyTorch. Here's a conceptual outline of such a class, demonstrating its methods and parameters. Download the code on OnePageCode Substack. This conceptual code snippet class provides a robust framework. The code snippet method sets up the window parameters and pre-calculates the indices for inputs and labels within each window. The code snippet method is the core logic for separating the input and label segments. Finally, code snippet and its properties code snippet leverages TensorFlow's efficient code snippet to generate the windows and then applies code snippet to create the final code snippet pairs. This structure ensures temporal integrity of data splits and efficient data loading. 13.5 Establishing performance baselines. Before investing significant time and computational resources into developing and training complex deep learning models, it is absolutely essential to establish baseline models. A baseline model provides a minimum performance threshold that any more sophisticated model must surpass to be considered useful. Without baselines, it's impossible to objectively assess whether your deep learning model is truly adding value or simply overfitting to noise. 3.5.1 Why baselines are crucial. Performance benchmark. Baselines define the floor for your model's performance. If your complex model doesn't beat a simple baseline, it indicates a fundamental issue, such as incorrect model design, poor data preprocessing, or even that the problem itself is not well suited for complex methods. Sanity check. They act as a sanity check. A model that performs worse than a naive forecast is effectively useless. Context for improvement. Baselines provide context for evaluating the magnitude of improvement. A 5% improvement over a naive baseline is more significant than a 5% improvement over an already sophisticated model. Resource allocation. If simple baselines perform exceptionally well, it might suggest that a complex deep learning solution is unnecessary, saving development time and computational cost. 3.5.2 Types of baseline models. Here are common types of baseline models used in time series forecasting, ranging from extremely simple to slightly more complex. Naive forecast, last value forecast. The simplest baseline, the naive forecast, predicts that the next value or sequence of values will be exactly the same as the last observed value in the input window. Description. For a given forecast horizon, it simply repeats the last known value from the input sequence. When to use. Excellent for time series that are very stable or have strong autocorrelation, i.e., the next value is highly dependent on the immediate previous value. It's always a good starting point. Conceptual logic. Download the code on OnePageCode Substack. This code snippet class illustrates how a baseline model would receive code snippet, a batch of input windows, and produce code snippet, a batch of label windows. It simply copies the last observed value from the input W. Indo across the entire forecast horizon. Simple moving average, SMA. The simple moving average baseline predicts the average of the last code snippet observed values in the input window. Description. Calculates the mean of a specified number of recent observations. When to use. Effective for time series with some volatility, but generally stable levels. It smooths out short-term fluctuations. Conceptual logic. Download the code on OnePageCode Substack. Simple linear regression. A simple linear regression model can be used as a baseline by fitting a line to the historical data within the input window and extrapolating it to predict the future. Description. Fits a linear relationship between time steps and observed values. When to use. Suitable for time series that exhibit a clear, consistent linear trend. Conceptual logic. For each window, it fits a simple code snippet model, where code snippet is the time index within the window, and uses this to predict future code snippet values. This would involve libraries like code snippet or code snippet. Simple feed-forward neural network, FFN. This serves as the most basic deep learning baseline. It's a fully connected neural network that takes the flattened input window as input and directly predicts the flattened label window. Description. A basic multi-layer perceptron, MLP, with 1 or 2 hidden layers. When to use provides a baseline that can capture some nonlinear relationships, serving as a first step into deep learning before employing more specialized architectures, RNNs, CNNs. Conceptual architecture. Input layer, size, code snippet. One or more code snippet, fully connected. Hidden layers with an activation function, e.g., relu. Output layer, size, code snippet, often with no activation for regression. Implementing and evaluating these baselines first allows you to understand the inherent predictability of your time series data and provides a crucial benchmark against which the performance of your more complex deep learning models can be truly measured. Creating windows of data. Deep learning models, particularly those designed for sequential data like recurrent neural networks, RNNs, long short-term memory, LSTM, networks, gated recurrent units, GRU, and transformers, have a fundamental requirement. They process data in fixed size, structured chunks. Unlike some traditional statistical methods that can directly consume an entire time series of varying length, deep learning architectures typically expect a consistent input shape. This necessitates a critical pre-processing step known as data windowing, where a continuous time series is transformed into a collection of input-output pairs, each representing a window of observations. Why deep learning models need windows? The necessity of data windowing for deep learning models stems from their architectural design and the way they learn from sequential dependencies. Fixed size inputs. Many deep learning models, especially those built for time series forecasting, are designed to accept inputs of a predefined, fixed length. For instance, an LSTM layer in a neural network expects each input sequence to have the same number of time steps. This fixed input size allows the model to be efficiently represented and processed by matrix operations within the neural network's layers. Each window, therefore, becomes a single training example, comprising an input sequence of a specific length and its corresponding target labels. Consider a scenario where you want to predict tomorrow. S-dot price based on the last 5 days of data. Your input sequence, the window, would always be 5 data points long. If you have 100 days of data, you would create many such 5-day windows, each serving as an independent training example for your model. Capturing sequential dependencies. Beyond fixed inputs, windowing is crucial for explicitly defining the temporal relationship between past observations, inputs, and future values, labels. Deep learning models learn these relationships by observing many such windows. Each window provides a snapshot of a sequence of events and their immediate consequence, allowing the model to generalize patterns over time. Without clearly defined windows, the model would struggle to understand which past observations are relevant for predicting a specific future point. Anatomy of a data window. Input sequence and target label. A data window fundamentally consists of 2 parts. 1. Input sequence features a contiguous block of historical data points that the model will use to make a prediction. This is often referred to as the look-back or input width. 2. Target labels. The future data points or sequence of data points that the model is trained to predict corresponding to the given input sequence. This is the look-forward or label width. The relationship between the input sequence and the target label is defined by an offset, which specifies the time gap between the end of the input sequence and the beginning of the target law. Bell. Numerical example of windowing. Let's illustrate with a simple time series representing daily temperature readings. Code snippet. Suppose you want to predict tomorrow's temperature using the last 3 days' data. Input width, 3 days. Label width, 1 day. Offset, 1 day, meaning the label is immediately after the input sequence. Here's how windows would be generated. Window index input sequence, X, target label, Y. 1 code snippet. 2 code snippet. 3 code snippet. 4 code snippet. 5 code snippet. 6 code snippet. 7 code snippet. Each row in this table represents a single training example for our deep learning model. The model will learn to map the patterns in the 3-day input sequences to their corresponding next-day temperatures. Introducing the code snippet class, a robust approach. Given the critical nature and potential complexity of data windowing, it is highly beneficial to encapsulate this logic within a dedicated class. A code snippet class serves as a robust, reusable component in your time series forecasting pipeline. It centralizes the parameters and methods related to creating, managing, and visualizing these windows, promoting code clarity, maintainability, and reusability across different projects. Conceptual design of code snippet. The primary purpose of COD. eSnippet class is to manage the transformation of raw time series data into the windowed format required by deep learning models. It should store key parameters that define the windows and provide methods to access the generated input label pairs. At a high level, the code snippet class will need to know the raw data it will operate on, how wide the input sequences should be, code snippet, how wide the label sequences should be, code snippet, the offset between the input and label sequences, code snippet, the columns to be used as features and labels. Basic class structure. Let's begin by outlining the initial structure of our code snippet class. This foundational setup will hold the essential configuration parameters for generating our data windows. Download the code on OnePageCode Substack. This initial code snippet method sets up the core parameters that define our data windows. It stores the code snippet, and the original code snippet. Importantly, it calculates code snippet, which is the span of time steps needed to extract one complete input label pair. It also predefines code snippet and code snippet to easily extract the relevant parts once a full window is formed. We also store code snippet for easy lookup of column positions. Benefits of a class-based approach. Using a class like code snippet offers several significant advantages. Encapsulation. All windowing logic, parameters, and even intermediate data, like processed windows, are contained within a single object, preventing global variable clutter and making the code more modular. Reusability. Once defined, the code snippet class can be easily reused across different time series datasets or forecasting projects, reducing redundant code. Maintainability. Changes or improvements to the windowing mechanism only need to be made in one place within the class, simplifying maintenance. Readability. The code becomes more intuitive. Instead of managing multiple lists and indices, you interact with a code snippet object. Extensibility. New functionalities, such as plotting windows or adding more complex windowing strategies, e.g., handling missing data within windows, can be easily added as methods to the class without affecting external code. Key parameters of windowing. Understanding the interplay of these parameters is crucial for effective data windowing. Input with code snippet. This parameter defines the number of past time steps the model will observe to make a prediction. Impact. A larger code snippet means the model has more historical context, potentially capturing longer-term dependencies. However, it also increases model complexity and computational cost. Too small in code snippet might miss crucial patterns. Considerations. This often depends on the periodicity of your data, e.g., if data has a weekly seasonality, and code snippet that covers at least 1 week might be beneficial, and the memory of your chosen deep learning. Model. Label with code snippet. This parameter specifies the number of future time steps the model is expected to predict. Single-step forecast. For predicting just the next single value, code snippet would be 1. Multi-step forecast. For predicting a sequence of future values, e.g., the next 24 hours, code snippet would be greater than 1. Considerations. The code snippet directly corresponds to the output shape of your deep learning model. Offset code snippet. The code snippet defines the gap between the end of the input sequence and the beginning of the label sequence. Impact. An code snippet of 0 means the label immediately follows the input. An code snippet of 1 means there's one time step between the end of the input and the start of the label. This is crucial for real-world scenarios where you might not have immediate access to the next value of prediction time. Example. If you predict tomorrow's stock price based on today's data, the code snippet is 1. Today's data ends. Tomorrow's price is the label. If you're predicting the next hour's temperature based on the last 5 hours, and you want to predict the temperature for the 6th hour, your code snippet is 1. Common pitfalls and best practices. Data leakage. A critical pitfall is allowing future information to leak into the training set. This can happen if windows are not correctly formed, or if data is scaled or normalized across the entire dataset before splitting into training, validation, and test sets. Always scale/normalize data using parameters derived only from the training set. Incorrect window sizes. Choosing code snippet and code snippet that are too large can lead to excessive memory consumption and longer training times. If too small, the model might not capture sufficient context. Experimentation and domain knowledge are key. Overlap versus non-overlap. Windows can overlap significantly, e.g., shifting by one time step for each new window, or be non-overlapping. Overlapping windows generate more training examples, but can introduce correlation between examples. For deep learning, overlapping windows, e.g., stride of 1, are standard as they provide a richer dataset for learning. Handling multiple features. When dealing with multivariate time series, multiple features, ensure all features are correctly windowed together for the input sequence, and the chosen label columns are correctly extracted for the output. The code snippet class will be extended to handle this. Temporal splits. Always split your time series data into training, validation, and test sets chronologically before windowing. This ensures that your model is always evaluated on unseen future data, mimicking real-world deployment. Windowing should then be applied within these split datasets. 3.1.1 Exploring how deep learning models are trained for time series forecasting. Deep learning models approach time series forecasting differently from traditional statistical methods. While models like ARIMA or exponential smoothing process the time series sequentially, often relying on past observations to predict the very next point, deep learning models require data to be structured into distinct input-output pairs, much like how they learn from images or text. This fundamental difference necessitates a crucial pre-processing step, data windowing. The necessity of data windowing for deep learning. Unlike traditional statistical models that inherently understand the sequential nature of a time series and process it point by point, deep learning models, particularly those designed for sequence data, like recurrent neural networks, RNNs, or transformers, need to be explicitly shown examples of sequences and their corresponding future values. This is achieved by transforming a single, long-time series into many shorter, overlapping sequences, known as windows. Each window serves as an independent training example. Consider a time series of daily temperature readings. A deep learning model doesn't just take the current day's temperature to predict tomorrow's. Instead, it learns to predict tomorrow's temperature, the label or target, by observing a sequence of past temperatures, the input. Understanding the sliding window mechanism. The core idea behind data windowing is the sliding window mechanism. This technique involves creating multiple input label pairs by sliding a window of a fixed size across the time series data. Each slide generates a new training example. Let's define the key parameters that govern this process. Code snippet, or code snippet. This is the length of the input sequence the model will observe to make a prediction. It defines how many past data points are included in the X part of a training example. Code snippet. This is the length of the sequence the model is expected to predict. It defines how many future data points constitute the Y part of a training example. For single-step forecasting, this would typically be 1. Code snippet, or code snippet. This parameter determines how many steps the window moves forward to generate the next input label pair. A code snippet of 1 is common, creating highly overlapping windows and maximizing the number of training examples. A larger code snippet creates less overlapping or even non-overlapping windows. Detailed walkthrough, generating windows. Imakin.team series dollar and havali a die a tree in dollar. To generate a single input label pair. 1. We select in code snippet number of consecutive data points, starting from some code snippet. This forms our input sequence $xt equals yt plus 1, yt plus backslash text input with $1. 2. Immediately following this input sequence, we select a code snippet number of consecutive data points. This forms our label sequence $yt equals yt plus backslash text input with yt plus backslash text input with plus 1, yt plus backslash text input with plus backslash text label with $1. 3. To generate the next pair, we slide the window forward by code snippet steps. If code snippet is 1, the next input sequence would start at $yt plus $1. This process continues until we reach the end of the time series, ensuring that there's enough data remaining to form both an input and a label window. Handling multiple features. In real-world scenarios, time series often have multiple features, e.g., temperature, humidity, wind speed. When creating windows, each time step within the window will consist of a vector of these features. For example, if we have daily temperature and humidity, and our code snippet is 3, an input window might look like code snippet. The model's input shape will typically be code snippet, where code snippet corresponds to code snippet and code snippet is the number of variables at each point in time. Concrete numerical example of windowing. Let's illustrate with a small numerical example. Suppose we have a time series, code snippet. We want to create windows where code snippet, use 3 past values. Code snippet, predict the next single value. Code snippet, slide by 1 position for each new example. Here's how the input label pairs would be generated. 1. Window 1. Input, code snippet. Label, code snippet. 2. Window 2. Shifted by 1. Input, code snippet. Label, code snippet. 3. Window 3. Shifted by 1. Input, code snippet. Label, code snippet. 4. Window 4. Shifted by 1. Input, code snippet. Label, code snippet. 5. Window 5. Shifted by 1. Input, code snippet. Label, code snippet. 6. Window 6. Shifted by 1. Input, code snippet. Label, code snippet. 7. Window 7. Shifted by 1. Input, code snippet. Label, code snippet. The process stops here because there aren't enough subsequent data points to form another label window after code snippet. From 10 data points, we generated 7 training examples. Pseudocode for sliding window generation. This pseudocode snippet demonstrates the fundamental logic for generating windows. Download the code on OnePageCode Substack. This function would produce results like those in our numerical example. This conceptual understanding is critical before implementing a more robust code snippet class. Implications of window sizes. The choice of code snippet and code snippet has significant implications. Computational cost. Larger code snippet values mean more data points per input sequence, leading to more complex models, e.g., LSTMs with more memory cells, and potentially higher computational costs during training. Ability to capture dependencies. A sufficiently large code snippet is necessary for the model to capture long-term dependencies in the data. If your patterns span several days, a code snippet of only a few hours might be insufficient. However, excessively large code snippet can introduce noise or irrelevant past information. Prediction horizon. Code snippet direct. LY determines the prediction horizon. A code snippet of 1 is for single-step forecasting, while larger values allow for multi-step forecasts, e.g., predicting the next 24 hours. Data utilization. A smaller code snippet, e.g., 1, maximizes the number of training examples generated from a given time series, which is beneficial for data-hungry deep learning models. However, it also creates highly correlated examples due to significant overlap. Other windowing strategies. While the code snippet overlapping window is very common for training, other strategies exist for specific use cases. Non-overlapping windows. Setting code snippet or code snippet for single-step labels creates distinct, non-overlapping windows. This can be useful for reducing autocorrelation between training examples, but significantly reduces the number of available samples. Varying stride. Using different code snippet values can be explored, though a code snippet of 1 is usually the default for maximizing data for training. Non-contiguous windows. More advanced techniques might involve selecting non-contiguous data points within a window, but this is less common for standard time series forecasting. Preparing data for deep learning models, batches, and epochs. Once the time series data is transformed into a collection of input label windows, it needs to be prepared for the deep learning training loop. This involves two core concepts, batches and epochs. Batches. Training deep learning models on individual examples one by one is computationally inefficient. Instead, models are typically trained on batches of data. A batch is a subset of the total training examples processed together. Purpose. Computational efficiency. Parallel processing of multiple examples on GPUs significantly speeds up training. Stabilized gradient updates. Using a batch to compute the gradient, how much to adjust model weights, provides a more stable estimate than using a single example, which can be noisy. Memory management. Larger models or datasets might not fit into memory as a whole, so processing in smaller batches is necessary. Input shape. When a batch of windows is fed to a deep learning model, the combined shape is typically code snippet. Code snippet. The number of individual window examples in the current batch. Code snippet corresponds to the code snippet of each window. Code snippet. The number of variables at each time step within a window. Epochs. An epoch represents one complete pass through the entire training dataset. During a single epoch, the model sees every training example exactly once, though the order might vary due to shuffling. Training process. Training typically involves multiple epochs. After each epoch, the model's performance on a separate validation set is usually evaluated to monitor for overfitting and determine when to stop training. The role of shuffling. Preserving order versus randomization. Shuffling data is a common practice in deep learning to prevent the model from learning the order of training examples and to ensure that each batch is representative of the overall dataset. However, with time series data, this must be handled carefully. Why not to shuffle within a data window? The sequential order of data points within an input window is paramount. Code snippet means something entirely different from code snippet. Shuffling within a window would destroy the temporal relationships the model is supposed to learn. This is a critical distinction from image or text data where the internal arrangement might be less strict. Why it is permissible to shuffle between data windows? Batches, once a time series has been transformed into independent input label windows. Each window represents a self-contained example of a sequence and its corresponding future. The relationship between code snippet, input code snippet, label code snippet, and code snippet, input code snippet, label code snippet, is that they come from the same underlying time series. However, for the purpose of training the model's weights, these distinct examples can be presented in any order. The model learns to map any input sequence of length code snippet to its corresponding code snippet future values, regardless of whether that input sequence came from early or late in the original time series. Shuffling the order of these independent windows, i.e., shuffling at the batch level, helps the model generalize better and prevents it from being biased by specific order in which the windows were originally generated from the time series. Conceptualizing the data window class. The concepts of windowing, batching, and conditional shuffling between windows, not within, are complex to manage manually. This is why a dedicated code snippet class becomes invaluable. Such a class would encapsulate all the logic required to 1. Take raw time series data. 2. Define code snippet, and code snippet parameters. 3. Generate all possible input label windows. 4. Handle splitting data into training, validation, and test sets. 5. Provide data in batches for efficient model training. 6. Manage shuffling at the batch level while preserving internal window order. By building a reusable code snippet component, we abstract away the intricate data preparation steps, allowing us to focus on designing and training the deep learning model itself. This sets the stage for a robust and scalable time series forecasting pipeline. 1.3.1.2 Implementing the data window class. After exploring the conceptual foundations of data windowing, we now transition to implementing a robust and reusable solution in Python. This section introduces the code snippet class, a central component in our time series forecasting pipeline. This class encapsulates all the logic required to transform raw time series data into the structured windows, input sequences, and corresponding label sequences that deep learning models expect. By the end of this section, you'll have a clear understanding of how to programmatically create these windows and prepare them into efficient TensorFlow datasets. Designing the code snippet class. The code snippet class is designed to be highly configurable, allowing you to define the characteristics of your input and label sequences, as well as the shift between them. It handles the crucial task of splitting your raw data into training, validation, and test sets, and then converting these into code snippet objects, which are optimized for deep learning model training. The core idea is to define a total window that slides across your time series. Within this total window, a portion is designated as the input sequence, features for your model, and another portion is designated as the label sequence, targets, that your model should predict. The code snippet parameter determines the temporal distance between the end of the input sequence and the beginning of the label sequence. Let's begin by outlining the initial structure of our code snippet class. Download the code on OnePatchCode Substack. Initializing the code snippet method. The code snippet method serves as the constructor for our code snippet class. It takes several parameters that define the characteristics of our data windows and the data sets they will operate on. Code snippet. The number of time steps in the input sequence, features that the model will see. Code snippet. The number of time steps in the output sequence, labels that the model will predict. Code snippet. The number of time steps between the end of the input sequence and the beginning of the label sequence. A code snippet of 1 means the label sequence immediately follows the input sequence. A code snippet greater than 1 implies a gap, useful for predicting further into the future. Code snippet, code snippet, code snippet. Pandas data frames containing the time series data for training, validation, and testing, respectively. These data frames should have a consistent set of columns. Code snippet, an optional list of column names that should be used as labels. If code snippet, all columns in the data frame are considered potential labels. This is crucial for multi-output forecasting, where you might want to predict multiple time series simultaneously. Within code snippet, we perform several critical calculations. 1. Column indexing. We create code snippet and code snippet dictionaries. These map column names, e.g., temp, temperature, humidity, to their integer index within the data frame. This allows for efficient data extraction by name rather than relying on brittle hard-coded indices. 2. Window parameters. The core windowing parameters, code snippet, code snippet, code snippet, are stored. 3. Total window width. Code snippet is calculated. This represents the total number of time steps in a single raw window extracted from the time series, encompassing both input and label parts, including any shift. 4. Code snippet objects for indexing. We define code snippet and code snippet using Python's built-in code snippet objects. A code snippet object, code snippet, is a powerful way to represent a range of indices. For code snippet means the input sequence starts at the beginning of the raw window, index 0, and extends up to, but not including, code snippet. For code snippet means the label sequence starts at code snippet, calculated as code snippet, and extends to the very end of the raw window. Code snippet indicates the end. Benefit of code snippet objects. Using code snippet objects makes the code more readable and reusable. Instead of repeatedly writing code snippet or code snippet, we can simply pass code snippet to extract the relevant portion of any window. This promotes clarity and helps prevent off-by-one errors. 5. Code snippet and code snippet. These number-py arrays store the relative indices within the code snippet that correspond to the input and label PA. RTS. While code snippet objects are used for the actual data extraction, these indices are useful for visualization and debugging to clearly show which time steps belong to the input and which to the label. Splitting windows into inputs and labels. The code snippet method. The code snippet method is crucial for transforming a raw window, a segment of the time series data of code snippet, into the distinct input features and target labels that a deep learning model expects. Download the code on OnePageCode Substack. Let's break down this method. 1. Code snippet input. This method receives a batch of raw windows, typically a TensorFlow tensor with shapecode snippet. 2. Slicing for inputs and labels. Code snippet. This line extracts the input sequence. The first code snippet indicates that we take all batches. Code snippet applies to the second dimension, time steps, selecting the code snippet steps at the beginning of each window. The last code snippet indicates that we keep all feature columns. Code snippet. Similarly, this extracts the label sequence using code snippet. 3. Handling multi-output labels. If code snippet is specified, meaning we want to predict a subset of the available features or multiple specific features, we use code snippet. This operation takes a list of tensors and stacks them along a new axis. Here, we iterate through the specified code snippet, extract the corresponding column from the code snippet tensor, and then stack them to form the final code snippet tensor. This is essential for models that predict multiple time series simultaneously. 4. Code snippet for performance and clarity. Code snippet and code snippet. These calls are crucial for TensorFlow's graph compilation. When TensorFlow builds its computation graph, it benefits from knowing the expected shapes of tensors. The first code snippet represents the batch size, which can vary during training, e.g., the last batch might be smaller. Code snippet and code snippet are fixed dimensions defined by our window parameters. The last code snippet represents the number of features, columns. This can also vary if we pass different data frames with different numbers of features, or if we select specific code snippet. While not strictly necessary for basic execution, code snippet helps TensorFlow optimize memory allocation and computation, potentially leading to faster training, and also makes debugging easier by providing clearer tensor shapes. Creating TensorFlow datasets, the code snippet method. The code snippet method is where the code snippet class truly leverages TensorFlow's powerful code snippet API. This method converts a pandas data frame into an efficient, batched, and optionally shuffled dataset suitable for deep learning model training. Download the code on OnePageCode Substack. Key aspects of code snippet. 1. Data conversion. The input data frame, code snippet, is first converted to a number-py array of code snippet. This is a standard practice, as TensorFlow operations typically work with number-py arrays or TensorFlow tensors. 2. Code snippet. This is a high-level utility function that simplifies the creation of sliding window datasets. Code snippet. The input time series data. Code snippet. This is a crucial point. While code snippet can generate targets directly, e.g., predicting the next single value, it is more flexible for complex windowing strategies like multi-step, multi-output, or with a code snippet to generate the raw total window and then use a code snippet function to split it into inputs and labels. By setting code snippet, the function simply returns windows of code snippet. Code snippet. This is set to code snippet, ensuring that each raw window contains enough data for both the input and label sequences, plus any shift. Code snippet specifies the number of windows to group into a single batch. Code snippet. For training datasets, shuffling the order of batches is generally recommended to prevent the model from learning spurious correlations based on data order. Distinction. It's important to note that only the order of the complete windows, batches, is shuffled. The chronological order within each window remains intact. This is acceptable for time series forecasting because the temporal relationships within a single input sequence are preserved, and shuffling batches merely changes the order in which these independent sequences are presented to the model. 3. Code snippet. After code snippet generates the raw windows, we use the code snippet method of the code snippet object. This applies our code snippet function to each window in the dataset. This is how the raw code snippet segments are transformed into the code snippet pairs expected by our deep learning models. Performance benefits of code snippet. Using code snippet with code snippet and code snippet offers significant performance advantages over manual Python loops for data preparation. Optimized data pipelining. TensorFlow's code snippet API is designed for high-performance data loading and pre-processing, leveraging C++ operations for efficiency. Parallelism. It can automatically parallelize data loading and transformations, overlapping data pre-processing with model training. Memory efficiency. Datasets can handle datasets larger than memory by streaming data from disk. Automatic batching/shuffling handles these operations efficiently without manual intervention. Convenient dataset access. Code snippet properties. To make it easy to access the prepared datasets, we define properties for code snippet, and code snippet. The code snippet decorator allows us to call a method like an attribute, making the code cleaner and more intuitive. Download the code on OnePageCode Substack. Now, instead of writing code snippet, you can simply write code snippet. This improves code readability and reduces verbosity. Visualizing data windows, the code snippet method. Visualizing the data windows is critical for debugging and understanding how your inputs and labels are aligned. The code snippet method helps confirm that your code snippet, and code snippet parameters are correctly configured. Download the code on OnePageCode Substack. Explanation of code snippet method components. 1. Code snippet property. This is a private attribute, indicated by the leading underscore, used for caching a single batch of data from the training set. Code snippet. This sequence of calls efficiently retrieves one batch. Code snippet gets the training dataset. Code snippet creates a new dataset containing only the first batch. Code snippet makes it an iterator, and code snippet retrieves the actual batch as TensorFlow tensors. Caching prevents reiterating the dataset every time code snippet is called, which can be computationally expensive. 2. Plotting logic. Code snippet and code snippet. Set up the figure and create multiple subplots to visualize several windows side by side. Code snippet controls how many sample windows are plotted. Code snippet retrieves the numerical index of the column we want to visualize, e.g., temperature, using code snippet. Plotting inputs. Code snippet draws a line representing the input sequence. Code snippet provides the x-coordinates, time steps relative to the window start. Code snippet extracts the data for the current sample, code snippet, all time steps, code snippet, and the specify. Ed column, code snippet. Code snippet. This parameter controls the drawing order. A lower code snippet means the element is drawn underneath others. Here, it ensures the input line is behind the scatter plots of labels and predictions, making them more prominent. Plotting labels, actual values code snippet plots the true label values as distinct scatter points. It handles the case where code snippet might not be one of the code snippet, preventing errors. Plotting predictions. If a code snippet is passed to the code snippet method, it makes a prediction on the code snippet and then plots these predictions as scatter points, allowing for a direct visual comparison with the actual labels. Code snippet, standard matplotlib functions for adding descriptive elements to the plot. Putting it all together, a complete code snippet class example. Here is the complete code snippet class, combining all the components discussed above. Download the code on OnePageCode Substack. Practical application and usage examples. To demonstrate the utility of the code snippet class, let's create some dummy data and walk through various common forecasting scenarios. First, let's set up some dummy data. Download the code on OnePageCode Substack. Example 1. Single-step forecasting. In single-step forecasting, We predict only the next single time step. This is a very common scenario. Download the code on one patch code Substack. In this setup, code snippet will be code snippet 24 time steps, 3 features, T, P, R, H, and code snippet will be code snippet 1 time step, 1 feature, T. Example 2. Multi-step, multi-output forecasting. This scenario involves predicting multiple future time steps for multiple variables simultaneously. Download the code on one patch code Substack. Here, code snippet will be code snippet, and code snippet will be code snippet 6 time steps, 2 features, T and P. Notice how code snippet correctly stacks the specified target variables. Example 3. Estimating maximum number of windows. It's often useful to know how many windows can be generated from a given dataset with specific window parameters. This can inform batching strategies or simply provide an understanding of the dataset size. Download the code on one patch code Substack. This function estimates the maximum number of windows, which can be useful for understanding the scale of your dataset. Example 4. Integrating code snippet into a simple Keras training loop. Finally, let's see how the code snippet class seamlessly integrates with a basic Keras model for training. Download the code on one patch code Substack. This snippet demonstrates the end-to-end utility of the code snippet class. You initialize it with your data and windowing parameters, and then simply pass code snippet and code snippet directly to code snippet. This greatly simplifies the data preparation pipeline, allowing you to focus on model architecture and hyperparameter tuning. The code snip ET method, when given the trained code snippet, immediately visualizes how well the model's predictions align with the actual labels. This code snippet class serves as a fundamental building block for all subsequent deep learning models we will explore, providing a consistent and efficient way to handle time series data. Applying baseline models. Before diving into complex deep learning architectures for time series forecasting, it is paramount to establish a performance benchmark. This benchmark is provided by baseline models. A baseline model is a simple, often non-learning, forecasting method that provides a minimal level of performance against which more sophisticated models can be compared. Without a baseline, it's impossible to determine if a complex model is actually adding value or simply overfitting noise. Consider it like this. If you develop a new trading strategy, you wouldn't just launch it without comparing its returns to a simple buy-and-hold strategy or a well-known index. Baselines serve that exact purpose in forecasting. There are buy and hold for model performance. The role of the code snippet class in baseline application. As we've explored in previous sections, the code snippet class is fundamental for preparing time series data for deep learning models. It transforms a flat time series into sequences of code snippets suitable for supervised learning. When applying baseline models, we will leverage this same structured data. The baseline model will take the code snippet generated by the code snippet and produce a code snippet that is then compared against the code snippet. Understanding forecast horizons and outputs. Time series forecasting problems can vary significantly based on what they aim to predict. These variations define different types of baseline models. And evaluation strategies. Single-step forecasting. In single-step forecasting, the goal is to predict the very next value in the sequence. This is the simplest form of forecasting. Concept. Given a window of past observations, e.g., the last code snippet hours of temperature data, predict the temperature for the next hour. Example. If your input window is code snippet, temperatures for the last 5 hours, a single-step model predicts code snippet, temperature for the current hour. Real-world application. Predicting the stock price for the next minute, the electricity demand for the next 15 minutes, or the next day's high temperature. Multi-step forecasting. Multi-step forecasting involves predicting multiple future values in a sequence. This is often more challenging as errors can compound over longer prediction horizons. Concept. Given a window of past observations, predict the values for the next M steps. Example. If your input window is code snippet, a multi-step model might predict code snippet, temperatures for the current, next, and day after next hours. Real-world application. forecasting weather for the next 7 days, predicting quarterly sales for the next year, or projecting energy consumption for the next 24 hours. Multi-output forecasting. Multi-output forecasting, sometimes called multivariate forecasting, involves predicting multiple different variables simultaneously for a given future time step or steps. Concept: given a window of past observa. Tie-ins for several related variables. Predict the future values for all those variables. Example: if your input window includes code snippet, a multi-output model might predict code snippet for the next time step. Real-world application: predicting both stock price and trading volume, forecasting temperature and wind speed, or simultaneously predicting the demand for different product categories. It's important to note that a multi-output model can also be single-step or multi-step regarding its time horizon. For instance, a model could predict code snippet, multi-output, single-step, or code snippet, multi-output, multi-step. Common baseline strategies. While there are many baseline strategies, we will focus on a few fundamental ones that are widely applicable and easy to implement. These baselines don't learn in the traditional sense. Instead, they apply simple rules to generate forecasts. 1. Naive, last observed value, forecast. This is the simplest baseline. It predicts that the next value will be the same as the last observed value. When to use. Ideal for time series that are very stable or exhibit random walk behavior. If there's no clear trend or seasonality and values fluctuate randomly around a mean, this can be surprisingly effective. Example: if yesterday's stock price closed at $100, the naive forecast for today's closing price is $100. 2. Mean/average forecast. This baseline predicts that the next value will be the average of all historical values in T. A training set, or a rolling average from the input window. When to use. Suitable for stationary time series with no apparent trend or seasonality, where values tend to revert to a mean. Less sensitive to recent fluctuations than the naive forecast. Example: if the average daily temperature over the last month was 25 degrees Celsius, the mean forecast for tomorrow's temperature is 25 degrees Celsius. 3. Seasonal naive forecast. This baseline predicts that the next value will be the same as the value from the same season in the previous cycle. When to use. Essential for time series with strong, regular seasonality, e.g., daily, weekly, monthly patterns. Example: if you're forecasting daily electricity consumption and last Monday's consumption was 1,000 megawatt hours, the seasonal naive forecast for next Monday's consumption is 1,000 megawatt hours. Implementing a naive, last observed value, baseline. Let's begin by implementing the simplest baseline, the naive, last observed value, forecast. This baseline is particularly useful for single-step forecasting and serves as a simple benchmark for any time series. We will use the code snippet output, which provides code snippet, the window of past data, and code snippet, the true future values we want to predict. The core idea is that for each input window code snippet, representing code snippet, our prediction for code snippet will simply be code snippet. First, let's set up some dummy data and a simplified code snippet output to illustrate. In a real scenario, this will come directly from your code snippet or code snippet. Download the code on one patch code substack. This initial code block sets up a small number py array to simulate the kind of code snippet and code snippet we would receive from our code snippets dataset. We've chosen a batch size of 3, a window width of 5, and a single feature to keep it simple. This setup is crucial for demonstrating how the baseline model will interact with data prepared by the code snippet. Now, let's implement the naive, last observed value, baseline. For a single-step forecast, this means taking the very last value from each input sequence as our prediction. Download the code on one patch code substack. Here, we define a simple code snippet class. It has a code snippet method that takes the code snippet from our code snippet output. The core logic is code snippet, which selects the last time step, code snippet, for all features, code snippet, across all items in the batch, code snippet. This effectively grabs the last observed value for each feature in each sequence, which is exactly what the naive forecast does for a single-step prediction. Let's compare these predictions with the actual labels to understand its performance. Download the code on OnePageCode Substack. This final segment prints out the actual labels alongside our naive predictions, allowing for a direct visual comparison. For our simulated data, the naive model predicts code snippet, while the actual values are code snippet. This simple comparison immediately highlights the error. In a real application, we would use quantitative metrics like mean absolute error, MFE, or root mean squared error, RMSE, to formally evaluate this error across the entire dataset, which will be covered in detail in subsequent sections. This concrete implementation demonstrates how a baseline model interacts with the code snippet's output. By establishing this simple benchmark, we create a critical reference point. Any deep learning model we develop must demonstrably outperform this naive baseline to be considered valuable. If a complex model cannot beat a simple last observed value forecast, it indicates a fundamental problem with the model, the data, or the problem formulation. Applying baseline models. After preparing our time series data using the code snippet class, the next crucial step in any machine learning workflow is to establish a performance benchmark. This benchmark is provided by a baseline model. A baseline model is typically a very simple, often non-machine learning, model that provides a minimum level of performance that any more complex model must surpass to be considered useful. It acts as a sanity check and helps us understand if our sophisticated deep learning models are actually learning anything meaningful beyond trivial patterns. The importance of a baseline model. Why dedicate time to a simple baseline when our goal is to build advanced deep learning models? Performance benchmark. It provides a concrete, quantifiable lower bound on performance. If a complex model performs worse than the baseline, it indicates a fundamental issue with the model, data, or training process. Sanity check. It confirms that the problem itself is not trivial or that our evaluation metrics are set up correctly. Context for improvement. The performance gap between the baseline and a more complex model quantifies the true value added by the complexity. Without a baseline, a mean absolute error of, say, 5 is just a number. With a baseline MA of 10, an MA of 5 looks excellent. If the baseline MA is 2, then an MA of 5 is poor. Starting point for iteration. It gives us a quick, initial understanding of the data's predictability before envies. Takes significant time in complex architectures. 4-time series forecasting. Common baseline strategies include last observed value. Naive forecasts predict that the next value will be the same as the most recently observed value. This is surprisingly effective for many stable time series. Mean/median forecast. Predict the average or median of all historical values or a rolling window of past values. Seasonal naive forecast. For data with strong seasonality, e.g., daily traffic, predict that the next value will be the value from the same period in the previous cycle, e.g., the traffic volume at 8 a.m. yesterday for 8 a.m. today. In this section, we will implement the last observed value baseline as it directly leverages the structure of our code snippet outputs. Recapping data window for single-step forecasting. Before defining our baseline model, let's briefly recall how the code snippet class prepares data for a single-step forecast. A single-step forecast predicts just one future value. This is achieved by setting code snippet and code snippet. The code snippet determines how many past time steps are used to make this prediction. We assume that the code snippet, and code snippet, our pre-split datasets, are available. These data frames contain the raw time series data, with columns representing different features. The code snippet dictionary, typically created from code snippet, helps us map column names to their integer indices, which is crucial for specifying which column to forecast. Let's instantiate a code snippet object for a single-step forecast. Download the code on OnePageCode Substack. The code snippet class is instrumental as it handles the complex task of transforming raw time series data into input label pairs suitable for deep learning models. For a single-step prediction of traffic volume, using in code snippet of 24, e.g., 24 hours of past data. Our code snippet would be configured as follows. Download the code on OnePageCode Substack. To understand the shape of the tensors that our baseline model will receive, let's grab a single batch from the training dataset and inspect its dimensions. Download the code on OnePageCode Substack. The output will show shapes like code snippet for inputs and code snippet for labels. This means for each of the 32 samples in the batch. Code snippet has 24 time steps, and each time step has 5 features. Code snippet has one time step, the predicted future value, and one feature, the traffic volume. Implementing the last observed value baseline model. Our baseline model will be a custom Keras model, subclassing code snippet. This approach allows us to define our own code snippet method for setup and, critically, our code snippet method, which contains the forward pass logic of the model. The last observed value baseline simply takes the last value from the input sequence for the target code snippet and uses it as the prediction for the next time step. Download the code on OnePageCode Substack. The code snippet method for our code snippet class is straightforward. It calls the constructor of the parent code snippet class using code snippet and stores the code snippet. This code snippet is crucial. It tells the model which specific feature, column, from the input sequence we're trying to predict. If code snippet is code snippet, it implies we want to predict all features available in the input. Now, let's define the code snippet method, which is where the core logic of our baseline model resides. This method defines how the model processes its code snippet to produce code snippet. Download the code on OnePageCode Substack. Let's break down the code snippet method. Code snippet. This tensor represents a batch of input sequences. Its shape is typically code snippet. Code snippet. This condition handles the scenario where we want to predict all features from the last input time step. Code snippet. This is a TensorFlow slicing operation. Code snippet selects all samples in the batch. Code snippet selects the last element along the code snippet dimension. The colon after code snippet is crucial. It ensures that the dimension is preserved. So if code snippet was 24, code snippet would select the 24th time step for all features, resulting in a shape like code snippet. This matches the expected output shape of our code snippet's labels, if code snippet were code snippet or all columns were selected. Code snippet. This handles the more common case where we are predicting a specific feature, e.g., traffic volume. Code snippet. This selects the value of the code snippet feature at the very last time step, code snippet, for all samples in the batch. The result of this slice would be a 1D tensor of shape code snippet. Code snippet. Keras models expect a consistent tensor shape for outputs, often including a time step dimension and a feature dimension, even for single values. Code snippet is used to insert a new dimension of size 1. The first code snippet transforms code snippet to code snippet. This new dimension can be thought of as the code snippet dimension, since our code snippet is 1 for single step. The second code snippet transforms code snippet to code snippet. This new dimension represents the number of label features, since we're predicting only one feature, traffic volume. This precisely matches the code snippet shape expected from code snippet. This careful manipulation of tensor shapes is fundamental in TensorFlow/Keras to ensure that data flows correctly between layers and that the model's output matches the expected label format for comparison during evaluation. Example, multi-output baseline. While our code snippet above targets a single label column, the code snippet class is flexible enough to handle multiple output predictions if code snippet is a list of indices. Let's consider how code snippet would behave for a multi-output scenario where code snippet is code snippet, e.g., predict, ing, traffic volume, and temperature. Download the code on OnePageCode Substack. When code snippet is a list, the code snippet method now loops through each index, extracts the corresponding last observed value, reshapes it to code snippet, and then code snippet joins these individual feature predictions along the last axis, resulting in a shape like code snippet, which is consistent with how code snippet would produce multi-output labels. Compiling the baseline model. Once the model architecture is defined, it needs to be compiled. Compilation configures the model for training and evaluation by specifying the optimizer, loss function, and metrics. Since our baseline model doesn't train in the traditional sense, it has no trainable parameters, the optimizer isn't strictly necessary, but code snippet is still required for evaluation. Download the code on OnePageCode Substack. Code snippet, MSE mean squared error, is a common loss function for regression tasks. It calculates the average of the squared differences between predicted and actual values. MSE heavily penalizes larger errors due to the squaring, making it sensitive to outliers. While our baseline isn't trained, specifying a loss function is standard practice for Keras models. Code snippet, MA mean absolute error, is another common metric for regression. It calculates the average of the absolute differences between predicted and actual values. ME is often preferred over MSE for interpretation because it is in the same units as the original data, making it more intuitive to understand the typical magnitude of error. It is also less sensitive to outliers than MSE. We use MAE here because it's a very interpretable metric for forecasting performance. Evaluating the baseline model. After compilation, we can evaluate our baseline model on the validation and test datasets generated by our code snippet. The code snippet method computes the loss and specified metrics. Download the code on OnePageCode Substack. The code snippet method returns a list where the first element is the loss, and subsequent elements are the values of the specified metrics in the order they were provided during compilation. Since we only provided code snippet as a metric, code snippet will give us the ME on the test set. Visualizing baseline predictions. Visualizing predictions is critical for understanding model behavior, especially for time series data. Our code snippet class includes a code snippet method designed to show inputs, true labels, and optionally, model predictions. By passing our code snippet model to this method, we can visually inspect how well the last observed value strategy performs. For visualization, it's often helpful to use a wide window that shows more context, e.g., 24 hours of input and 24 hours of labels, even if we only predict one. This allows us to see the trend leading up to the prediction and the actual values that follow. Download the code on OnePageCode Substack. The plot generated by code snippet will display several examples. For each example, you will see input sequence, the past 24 hours of traffic volume, and other features, though only traffic volume is typically highlighted for prediction. True labels, the actual traffic volume values for the next 24 hours. Baseline predictions. Since the baseline predicts the last observed value, you will see a horizontal line extending from the end of the input sequence, representing this constant prediction for all future time steps within the label window. This clearly illustrates the simplicity and limitations of this baseline. Interpreting baseline performance. The mean absolute error, ME, value printed for the baseline model is our first concrete benchmark. For example, if the baseline MAE is code snippet, it means, on average, our last observed value prediction is off by 150 units of traffic volume. What does this tell us? This MA value is the lowest acceptable performance. Any more complex deep learning model we build must achieve an MA significantly lower than 150 to be considered worthwhile. If a sophisticated model yields an MA of 160, it means it's performing worse than simply guessing the last observed value, indicating a problem. When might this baseline perform well or poorly? Well, for very stable time series with low volatility and strong autocorrelation, where the next value is indeed very close to the current one. Examples might include slow-changing tempi, retour readings over short periods. Poorly, for highly volatile, noisy, or rapidly changing time series. If the traffic volume fluctuates wildly hour to hour, predicting the last hour's value will frequently be inaccurate. It also performs poorly for series with strong trends or seasonality that are not captured by simply taking the last value. The baseline serves as a critical first step. It grounds our expectations and provides a clear target for improvement. With this foundation, We are now ready to explore more complex deep learning architectures that can learn intricate patterns and potentially outperform this simple yet powerful benchmark. 3.2.2 Multi-step baseline models. Establishing robust baseline models is a crucial first step in any time series forecasting project. For multi-step forecasting, where we predict multiple future time steps, these baselines provide fundamental benchmarks against which more complex deep learning models can be measured. They help us understand the inherent difficulty of the forecasting task and whether our sophisticated models are truly adding value beyond simple heuristics. This section will demonstrate how to implement two common multi-step baseline models using TensorFlow/Keras and the code snippet class we developed previously. 1. Last value baseline. Code snippet predicts the last observed value from the input sequence for all future time steps. 2. Repeat input baseline. Code snippet repeats the entire input sequence for the duration of the prediction window. These baselines, while simple, provide insights into data characteristics like stationarity and seasonality. If a complex model fails to outperform these simple baselines, it's a strong indicator that the model design, training, or data preparation needs reevaluation. Configuring the data window for multi-step forecasting. Before defining our baseline models, we need to configure our code snippet object to handle multi-step forecasting. This involves specifying in code snippet how many past time steps to consider, a code snippet how many future time steps to predict, and a code snippet the offset between the E and D of the input and the start of the labels. For multi-step prediction, it's common to set code snippet equal to code snippet. This ensures that the prediction window immediately follows the input window without any gap. Download the code on OnePageCode Substack. In this code, we set up a code snippet instance named code snippet. We specify in code snippet of 24, e.g., 24 hours of data, a code snippet of 24, predicting the next 24 hours, and a code snippet of 24. A code snippet equal to code snippet is typical for contiguous multi-step predictions, meaning the prediction window begins immediately after the input window ends. The code snippet argument ensures that our models focus on predicting the specified feature, code snippet in this case. The printed shapes confirm that our input and label tensors are now designed for multi-step sequences. Implementing the multi-step last baseline model. The code snippet model is conceptually very simple. For every time step in the prediction horizon, it outputs the last observed value from the input sequence. This baseline is particularly useful for data that is relatively stationary or changes slowly over time. We implement this as a custom Keras code snippet by subclassing code snippet and overriding its code snippet and code snippet methods. Download the code on OnePageCode Substack. The code snippet class extends code snippet. In its code snippet method, it first extracts the last observed value for the target feature from the input sequence. The code snippet is critical here. If our input has multiple features, but we only predict one, e.g., temperature, this index ensures we extract the correct feature. If code snippet is code snippet, it means we are predicting all features. The core of this model is the code snippet operation. Let's break down code snippet. Code snippet. This is our tensor with shape code snippet, or code snippet if code snippet is specified. It holds the last value for each batch. Code snippet. This code snippet argument tells code snippet how many times to repeat code snippet along each dimension. Code snippet. Do not repeat along the batch dimension. Code snippet. Repeat code snippet times along the time dimension, which is currently 1. If code snippet is 24, this effectively expands the time dimension from 1 to 24. Code snippet. Do not repeat along the feature dimension. The result is a tensor of shape code snippet, where each element along the code snippet dimension is the same last observed value. Implementing the repeat baseline model. The code snippet model takes the entire input sequence and repeats it to form the prediction sequence. This baseline is particularly effective for data with strong seasonality, where patterns tend to recur over fixed intervals, e.g., daily or weekly cycles. Download the code on one-page code Substack. The code snippet also extends code snippet. Its code snippet method first selects the relevant features from the input sequence. CR. Usually, if only a single code snippet is specified, code snippet is used to restore the feature dimension, ensuring the tensor remains 3D code snippet. The repetition logic is more involved here. We calculate code snippet by dividing code snippet by code snippet and taking the ceiling. This tells us how many times the entire input sequence needs to be repeated to cover the code snippet. For example, if code snippet and code snippet is 1. If code snippet is 2. The code snippet operation then repeats the code snippet tensor code snippet times along the time dimension. Finally, the result is slice code snippet to ensure the output tensor's time dimension exactly matches code snippet, effectively truncating any excess repeated data. Model instantiation, compilation, and evaluation. With our baseline models defined, the next step is to instantiate them, compile them with a loss function and metrics, and then evaluate their performance on the validation and test datasets provided by our code snippet. We will use mean squared error, MSE, as the loss function and mean absolute error, ME, as the evaluation metric. ME is often preferred for time series forecasting as it is more interpretable, representing the average magnitude of errors in the same units as the target variable. Download the code on one-page code Substack. In this block, we first create instances of both code snippet and code snippet, passing the code snippet to ensure they predict the correct feature. Each model is then code snippeted with code snippet as the loss function and code snippet as the metric. The code snippet method is called on the code snippet and code snippet datasets. The code snippet argument prevents the progress bar and per batch output from being printed, resulting in a cleaner output for the final performance metrics. Comparing baseline performance. To easily compare the performance of our two multi-step baselines, let's print their test MAE side by side. Download the code on one-page code Substack. This summary table provides a quick overview of how each baseline performed on the unseen test data. The choice of which baseline performs better often depends on the underlying characteristics of the time series data. For example, if the data has a strong daily or weekly seasonality, the code snippet might outperform code snippet. If the data is more random or slowly varying, code snippet might be sufficient. Visualizing multi-step predictions. Visualizing the predictions of these baseline models against the actual values is incredibly insightful. The code snippet class provides a convenient code snippet method for this purpose, allowing us to see how well or how poorly these simple strategies capture the future trend. Download the code on one-page code Substack. The code snippet method generates plots for a few example batches from the test set. When plotting code snippet, you'll typically observe a flat line for the prediction, as it simply repeats the last known value. For code snippet, you'll see the input pattern being replicated, which can visually align well with seasonal data. These visualizations are crucial for understanding the behavior and limitations of each baseline. Examining raw predictions, optional. To further understand what the baseline models are outputting, we can use code snippet on a single batch from our dataset. This allows us to inspect the raw tensor output. Download the code on one-page code Substack. This code snippet takes one batch of data from the validation set and feeds it into both code snippet and code snippet using code snippet. By printing the input, actual labels, and the raw prediction for the first example in the batch, you can directly observe how code snippet produces a constant value across the prediction horizon, while code snippet replicates the input pattern. This reinforces the understanding of how code snippet operates in each case. Saving and loading baselines, optional. While these simple baselines don't require complex saving/loading procedures like deep learning models with learned weights, Keras provides a consistent API. Download the code on one-page code Substack. Saving and loading custom Keras models requires slightly more care than standard layers, as Keras needs to know how to reconstruct your custom class. For these simple baselines, saving and loading only the model weights, code snippet, is often sufficient, as they have no TR. Enable parameters. If you were to save the entire model, e.g., code snippet, you would typically need to register your custom classes using code snippet when loading. These multi-step baselines provide a fundamental starting point for evaluating the performance of more complex deep learning models in time series forecasting. They serve as essential benchmarks, helping to ensure that sophisticated models truly learn meaningful patterns beyond simple repetitions or last value predictions. 3.2.3 Multi-Output Baseline Model. Time series forecasting problems often involve predicting not just a single future value, but multiple related future values simultaneously. For instance, in a smart city context, you might want to predict both future traffic volume and ambient temperature, as these two variables are often correlated and can influence each other. A multi-output time series model is designed to handle such scenarios, producing predictions for several target variables at once. Just as we established single-step and multi-step baselines, it's crucial to define a multi-output baseline. This provides a fundamental benchmark against which more complex deep learning models can be evaluated. A simple yet effective multi-output baseline can be constructed by extending our last known value strategy. For each target variable, we predict its last observed value from the input sequence, preparing data for multi-output forecasting. The code snippet class, which we designed for flexibility, can easily be configured to handle multiple output variables. Instead of providing a single column name or index to the code snippet parameter, we simply provide a list of the column names we wish to predict. Let's first define our column indices for clarity, as this will be used by our code snippet and code snippet models. Download the code on OnePageCode Substack. Now, we initialize two code snippet instances, one for a single-step multi-output forecast and another for a wide multi-step multi-output forecast. Notice how code snippet is a list containing code snippet and code snippet. Download the code on OnePageCode Substack. The output of the code snippet for multi-output problems will be code snippet, where both code snippet and code snippet are TensorFlow code snippet objects. The key difference is in the shape of the code snippet tensor. For a multi-output scenario, if code snippet is the batch size, code snippet is the code snippet, and code snippet is the number of code snippet, the code snippet tensor will have a shape of code snippet. This means for each example in the batch, and for each time step in the code snippet, there will be code snippet predictive values, one for each target variable. For instance, consider an example from code snippet. Download the code on OnePageCode Substack. In this output, code snippet indicates a batch of 256 examples, each with 24 input time steps and 19 features. Code snippet indicates a batch of 256 examples, each predicting 24 future time steps, with two target variables, code snippet and code snippet, at each time step. The code snippet will show two values, corresponding to code snippet and code snippet at the first predicted time step. The code snippet class for multi-output predictions. Our code snippet model, defined in a previous section, was designed with multi-output capabilities in mind from the start. This design choice highlights the power of flexible class definitions. By checking the type of code snippet in its code snippet method, the code snippet class can gracefully handle both single integer indices for single output problems and lists of indices for multi-output problems. Here's the relevant part of the code snippet class definition again, with emphasis on the multi-output logic. Download the code on OnePageCode Substack. Explanation of tensor manipulation, code snippet and code snippet. When dealing with multi-output and potentially multi-step forecasting, ensuring the output shape of your model matches the expected shape of the true labels is crucial for Keras' code snippet, and code snippet methods. Let's trace the shapes in the code snippet branch. 1. Code snippet. Code snippet has shape code snippet. Code snippet extracts the last time step for all features, resulting in code snippet. By indexing with code snippet, which is a list of column indices, we select only the relevant target features. Resulting shape, code snippet. For code snippet, this would be code snippet. 2. Code snippet. Code snippet inserts a new dimension of size 1. Here, it's inserted between the batch dimension and the code snippet dimension. This effectively changes the shape from code snippet to code snippet. This code snippet represents the code snippet for a single-step prediction. 3. Code snippet. Code snippet takes a tensor and repeats it according to the code snippet argument. Code snippet has shape code snippet. Code snippet means repeat 1 ton, IME along the first dimension, batch size. Repeat code snippet times along the second dimension, the one we just added with code snippet. Repeat 1 time along the third dimension, number of targets. If code snippet is 24, as for code snippet, the shape becomes code snippet. This perfectly matches the code snippet shape generated by code snippet. This revised code snippet class is now robust enough to serve as a multi-output, multi-step baseline, always matching the code snippet specified by the code snippet. Implementing and evaluating the multi-output baseline model. Now we can instantiate, compile, and evaluate our code snippet model using the multi-output code snippet. We need the integer indices for traffic volume and temp. Download the code on one patch code substack. The code snippet might not show detailed layer information for a simple code snippet subclass without explicit code snippet. It primarily confirms it's a Keras model. Next, we evaluate the model on the validation and test sets. Download the code on one patch code substack. When code snippet is called on a multi-output model with a single code snippet metric, Keras typically calculates the MD for each output dimension, e.g., code snippet and code snippet in our case, and then averages them to provide a single scalar value for the overall ME. This single ME value represents the average absolute error across all predicted targets and all time steps in the code snippet. To get individual MEs per target, you would generally need to define custom metrics or perform separate evaluations for each target, which can be more complex. For benchmarking, the aggregated ME serves its purpose effectively, visualizing multi-output predictions. The code snippet method is versatile enough to visualize predictions from multi-output models. By default, it plots the first column specified in code snippet. However, you can explicitly tell it which column to plot using the code snippet argument. First, let's visualize the predictions for code snippet. Download the code on one patch code substack. Now, let's explicitly plot the predictions for code snippet. Download the code on one patch code substack. These plots visually confirm that our multi-output baseline model simply predicts the last known value for each target variable across the entire prediction horizon. This clearly demonstrates the simplicity of the baseline and provides a visual reference for how much more sophisticated models will need to improve. Alternative multi-output baseline, mean prediction. While the last known value is a common baseline, another simple strategy for multi-output problems is to predict the mean of the input sequence for each target variable. This can sometimes be a stronger baseline, especially if the time series is stationary or exhibits strong mean reversion. Let's implement a code snippet to illustrate this concept. Download the code on one patch code substack. Comparing the performance metric. S of the last known value baseline and the mean baseline provides a more comprehensive understanding of the problem's inherent predictability. If the mean baseline performs significantly worse than last known value, it might indicate strong temporal dependencies. If it performs similarly or better, it could suggest less volatile or more stationary series. Practical considerations for multi-output models. When developing multi-output time series models, several practical aspects warrant attention. 1. Target scaling. If your target variables have vastly different scales, e.g., traffic volume in thousands and temperature in tens, it is often beneficial to normalize or standardize them. This prevents one target with larger numerical values from dominating the loss function and model training process. While our baseline models don't learn parameters, this is a critical step for deep learning models. 2. Differing importance of targets. In some applications, certain target variables might be more critical to predict accurately than others. Standard loss functions, like MSE, treat all targets equally. If specific targets are more important, You might need to use weighted loss functions or define custom loss functions that penalize errors on critical targets more heavily. 3. Specialized loss functions. For certain types of multi-output problems, domain-specific loss functions might be more appropriate. For example, if predicting a probability distribution across multiple CA categories, cross-entropy loss would be used. 4. Real-world applications. Multi-output forecasting is prevalent in various fields. Healthcare, predicting multiple vital signs, heart rate, blood pressure, oxygen saturation, from a patient's continuous monitoring data. Finance, forecasting multiple related economic indicators, inflation, GDP growth, interest rates, or predicting the prices of several correlated stocks. Energy, predicting electricity demand, gas consumption, and renewable energy generation simultaneously for grid management. Retail, forecasting demand for several related products, e.g., different sizes of the same apparel item, to optimize inventory. Understanding and implementing these simple multi-output baselines is a fundamental step. They highlight the minimum performance expectation and provide a crucial reference point before delving into more complex deep learning architectures capable of capturing intricate cross-series dependencies and nonlinear patterns. Summary. This section consolidates the fundamental concepts and practical tools introduced in the preceding discussions, reinforcing the critical role of data preparation and evaluation in time series deep learning. We revisit the indispensable technique of data windowing, the utility of our custom code snippet class, and the rationale behind selecting specific loss functions and evaluation metrics. Data windowing, transforming time series for deep learning. Deep learning models, by their nature, excel at learning patterns from fixed-size input tensors. Time series data, however, is inherently sequential and often variable in length. Data windowing acts as a crucial bridge, transforming continuous time series into a supervised learning problem where past observations, the input window, predict future observations, the output window. This transformation is analogous to sliding a fixed-size frame across a video stream. Each frame captures a segment of action, which can then be used to predict the next segment. In time series, each frame becomes a training example, consisting of a sequence of features, e.g., past temperatures, stock prices, and their corresponding target values, e.g., future temperatures, stock prices. The core idea is to create pairs of code snippet from a single long time series. This process is essential for deep learning models like recurrent neural networks, RNNs, and transformers, which require structured input-output pairs for training. The versatility of the code snippet class. To streamline the intricate process of data windowing, we developed the code snippet class. This custom utility is more than just a wrapper. It's a robust and reusable component designed to handle various time series forecasting scenarios with remarkable flexibility. Its primary advantage lies in abstracting away the complexity of slicing, batching, and shuffling time series data, allowing us to focus on model development rather than data wrangling. The code snippet class is particularly adept at adapting to different forecasting horizons and output requirements, which were explored in detail in previous sections. Let's briefly recall its adaptability. Single-step forecasting. For single-step forecasting, the code snippet prepares input sequences to predict a single future value. This is the most straightforward application, where the model learns to predict the next time step based on a window of historical data. Download the code on OnePageCode Substack. The code snippet class, as simplified above, encapsulates the logic for creating input-output pairs. The code snippet method is key, separating the input features from the target labels based on the code snippet and code snippet. Download the code on OnePageCode Substack. Here, code snippet signifies a single-step prediction. The code snippet indicates that we are predicting the very next time step immediately following the input window. Multi-step forecasting. For multi-step forecasts, the code snippet is configured to predict multiple future values sequentially. This is achieved by setting code snippet to a value greater than 1, allowing the model to generate a sequence of predictions. Download the code on OnePatchCode Substack. In this configuration, the code snippet is set to 5, meaning each training example will consist of an input sequence of 20 time steps and a target sequence of 5 future time steps for code snippet. Multi-output forecasting. Beyond predicting multiple future steps of a single variable, the code snippet also supports multi-output forecasting, where the model predicts multiple variables simultaneously for a given future horizon. This is handled by specifying multiple column names in code snippet. Download the code on OnePatchCode Substack. By passing a list of column names to code snippet, the code snippet ensures that the target labels for each window include data from all specified columns, enabling models to learn relationships and predict multiple time series concurrently. This reusability significantly simplifies the data preparation phase for diverse forecasting tasks. Loss functions, mean squared error, MSE. In the context of training deep learning models for regression tasks like time series forecasting, a loss function quantifies the discrepancy between the model's predictions and the actual target values. The model then uses this quantified error to adjust its internal parameters during training. We primarily chose mean squared error, MSE, as our loss function. MSE calculates the average of the squared differences between predicted and actual values. The formula for MSE is $MSE in havali vrak v'invin simbi in havali infin I hafi dui $. Where $& is the number of data points. $E is the actual value. $hat $Y is the predicted value. Download the code on OnePatchCode Substack. The output will show the computed MSE value. The code snippet function provides a convenient way to compute this loss. Advantages of MSE. 1. Penalizes large errors more heavily. Due to the squaring operation, larger errors contribute disproportionately more to the total loss. This makes MSE sensitive to outliers and encourages the model to minimize significant deviations, which is often desirable in financial or critical infrastructure forecasting where large errors can have severe consequences. 2. Differentiable and convex. MSE is a convex function, which makes it well suited for optimization algorithms like gradient descent. Its derivative is continuous, allowing for smooth and efficient convergence during model training. Considerations. While beneficial for penalizing large errors, MSE sensitivity to outliers can also be a disadvantage if the dataset contains extreme, anomalous values that are not representative of the underlying process. These outliers can heavily influence the model's learning, potentially leading to a biased model. Evaluation metrics, mean absolute error, MAE. While MSE is excellent for optimizing the model during training, it can be less intuitive for human interpretation due to the squaring of errors. For evaluating model performance and understanding its typical prediction accuracy, we often turn to mean absolute error. MAE calculates the average of the absolute differences between predicted and actual values. The formula for MAE is $MAE in havali vrak vinfin simbi in havali invin I hafe $. Where $& is the number of data points. $E is the actual value. $hat $Y is the predicted value. Download the code on OnePatchCode Substack. The output will display the computed MAE value. Code snippet is used as a metric to track during training and evaluation. Advantages of MAE. 1. Ease of interpretation. MAE is directly interpretable in the same units as the target variable. For example, if forecasting stock prices, an MAE of 50 cents means that, on average, the model's predictions are off by 50 cents. This makes it a very intuitive metric for stakeholders and non-technical audiences. 2. Robustness to outliers. Unlike MSE, MAE is less sensitive to outliers because it does not square the errors. A large error from an outlier contributes linearly to the total MAE, preventing it from excessively skewing the overall performance assessment. This is particularly useful in datasets prone to extreme but rare events. The synergy of MSE and MAE. The choice of MSE as a loss function and MAE as an evaluation metric is a common and effective strategy in time-SARE. IES forecasting. MSE's strong penalty on large errors helps guide the model towards a solution that minimizes significant deviations during the training process, leading to more stable and robust learning. Concurrently, MAE provides a clear, interpretable measure of the typical prediction error, giving us a practical understanding of the model's performance in real-world terms. In essence, MSE acts as the optimizer's guide, pushing the model to reduce all errors, especially the large ones, while MAE serves as the user's report card, offering an easily digestible summary of the model's average accuracy. This dual approach ensures both effective model training and transparent performance reporting.